Alright guys, so sorry again that I couldn't be here in person, but I am here with you in spirit and voice to give you this awesome lecture on types of chemical reactions. So here we go. So when we're talking about chemical reactions, basically there's two main ways to classify different types of chemical reactions. One, you can take a look at what the atoms actually do. Are they combining together to make something new? Are they breaking apart to make something new? Or are they simply just rearranging and changing their partners to make a new product? Or the second way to kind of classify chemical reactions is by what kinds of chemistry or phenomena take place. So is something dissolving, or is a precipitate forming from two liquids, meaning is there now some kind of solid that forms? Is it an acid-base reaction? Is there gas bubbles that are being evolved from it? Or is it like a redox reaction where you have the exchange of electrons, and we see that in a particular way as well. All right, so there's two kinds of ways that we classified. When you guys took regular chemistry, we were mostly talking about number one, by what the atoms do: combining, breaking apart, rearranging. Because remember, those were single replacement, double replacement, synthesis, and decomposition. Here in dual chem, we're going to talk about both kinds. We're going to talk about what the atoms do and the kind of chemistry that it takes part in some chemical reactions. All right, so before we talk about specific types of chemical reactions, first let's talk about aqueous solutions, because the most common chemical reactions, and most of the chemical reactions that are going to take place, especially in the lab and also in the real world, are when at least one of the substances is in an aqueous solution. So what is an aqueous solution? It's a homogeneous mixture of a substance with water. So basically it's whatever substance we're talking about mixed with water. So for example, sodium chloride, an aqueous solution of sodium chloride would have table salt, sodium chloride, dissolved in water. So let's take a moment to see what actually happens when substances are dissolved in water. So if you're looking at a ionic compound like sodium chloride, when ionic compounds dissolve in water, they dissociate into their ions. So sodium chloride is made out of a sodium ion with a positive charge and chlorine ion with a negative charge. And remember, that's because the sodium is going to give his valence electron to chlorine, and so he loses one, becomes a positive one charge. Chlorine gains one, becomes a negative one charge, and usually the positive and negative electrostatic force is going to hold them together, except in water. Okay, so in water, the H2O molecule also has positive and negative charges on in its molecule, and so they're going to tear basically the sodium and the chlorine from each other, and so that's what we call dissociation. So you can see, in this picture right here, the the oxygen of the water molecule is slightly negative, and so that's going to be tugging on the positive sodium ion, and the hydrogens of the water have a slightly positive charge, so they are going to tug on the chlorine ions, and eventually you're going to get the sodium ions, okay, that are pulled away from the chlorine ions, and they're all going to be basically surrounded by little water molecules. So that's what happens when you actually dissolve or ionic compounds. They dissociate. Now, not all ionic compounds are going to dissociate or dissolve in water. So salt definitely does. You put a teaspoon of salt in water, stir it up, bam, it disappears. But not all substances do. Sometimes you'll put a substance in water, stir it up, and it just kind of either floats there or it all sinks to the bottom. So the substances that completely dissociate into ions are what we call strong electrolytes. Okay, they can, and these guys can conduct electricity. Why? Well, remember, we've got charged particles, and anytime you have charged particles, you can conduct electricity. Because electricity is basically just electrons jumping from one atom or ion to another. So solutions that contain free moving particles, like these strong electrolytes, these substances that dissociate in water, are going to be able to conduct electricity. So if you stick a light bulb in there with some leads in it, the light bulb will definitely light up. Now, sodium chloride is a very strong electrolyte, but there's also weak electrolytes, meaning that they'll dissociate but not fully dissociate. So sodium chloride will dissociate, and all of the sodium is going to break apart from all of the chlorine ions. And so all of them will be free floating in the liquid. However, there are some that are called weak electrolytes because not all of their ions are going to break apart. So these guys are going to basically have kind of stronger electrical forces that keep those molecules together and don't allow water to break them all apart. So they're going to have some free moving particles, but not as much as the strong electrolytes. And then finally, there are some substances, obviously, that we can dissolve in water, and they don't conduct electricity at all. And so this is going to be like sugar. Sugar dissolves in water. And the way it does that is by breaking intermolecular forces, not actually breaking apart ions, because remember, sugar is covalent, and they are held together by sharing electrons, not by transferring electrons and then having an electrostatic force hold them together. So when sugar breaks apart, their molecules are not charged, and so there are no charged molecules or charged particles floating around, and so they are not going to conduct electricity at all. So if you put a light bulb in sugar water, the light bulb will not conduct electricity at all. It will not light up. All right, so what if you have a compound that has a polyatomic ion in it, like sodium nitrate here, NaNO3? Well, when it dissolves in water and becomes an aqueous solution, the polyatomic ion is going to stay intact. Okay, so that's kind of key. Polyatomic ion stays intact. So what's going to break apart is the Na is going to break apart from the NO3 molecule. Okay, so sodium has a positive charge, NO3 has a -1 charge, and that's how it's going to split up. Positive charge of the Na, okay, the sodium, and then the NO3 clumps together and it still has its negative charge. All right, there are some ionic compounds, though, that do not dissolve in water. Basically, the electrostatic, one way we can think about it is the electrostatic force between these guys is so strong that it doesn't let water break it apart. And so silver chloride is an example of a substance that does not dissolve in water. So this obviously would be one that does not light up a light bulb. So we can see here in this illustration that high solubility, okay, is which we'll get to in just a second. Solubility means you can dissolve in water. So high solubility compounds are going to be able to break apart into their charged particles, and low solubility ones, you can see here, are just going to clump together and stay together in water. So usually they'll either float on top or just sink right to the bottom. All right, so I had mentioned it in the previous slide, and here it is officially. Solubility. Okay, that is basically our fancy word in chemistry for being able to dissolve in water. So a compound that is soluble is able to dissolve in water. And a compound that is insoluble, okay, note the prefix in, which means without, is not able to dissolve in water. Okay, so this guy would be soluble, and this guy here that clumps together still would be insoluble. So that's the two kind of vocabulary words that we use quite often when we're talking about being able to dissolve in water. Soluble means you can, insoluble means you cannot. All right, so we have come to the fun, because at this level we get to basically learn how we can tell if substances will be able to dissolve in water or not. And guess what? There is no easy way, but there is this handy dandy chart for solubility rules. And guess what? You do not need, let me rephrase, you do not need to memorize this. Okay, you will have this on tests and quizzes. You just need to know how to use it and remember to use it when you are working with some problems. Okay, so these are the solubility rules for ionic substances. So if you take a look, compounds, so the first part, obviously, these guys are able to dissolve. Okay, so these guys are dissolvable. All right, and so compounds containing alkali metals, all right, remember those are the ones in the first group on the periodic table: lithium, sodium, potassium, rubidium, cesium, right, and the ammonium ion. These guys are always soluble, so no matter what they're hooked up with, they are going to be soluble. Nitrates, bicarbonates, and chlorates are also soluble, so no matter what they're hooked up with, they are able to dissolve in water. Now the halides, okay, so those are the halogen group, group 7, okay. Chlorine, bromine, and iodine are generally soluble, except you see here we have some exceptions. So if chlorine, bromine, or iodine is hooked up with any of these three guys, they are insoluble. So the silver chloride that we saw earlier in the lecture, we said that was insoluble. Okay, so that's because this chlorine is hooked up with silver. There's also, it looks like mercury and lead compounds that are with halogens are also insoluble. Sulfates are generally soluble except those that are hooked up with these metals. Okay, so silver, calcium, strontium, barium, mercury, and lead. All right, those guys would be insoluble. Now, if we take a look at the guys that are generally insoluble, so not dissolvable down here, bam. Carbonates are usually not soluble. Phosphates, chromates, and sulfides are usually not soluble, except, again, we always have exceptions, except if they are hooked up with any of those alkali metal ions and ammonium. Okay, so basically if it's hooked up with these guys, all right, they're still soluble. But, you know, calcium carbonate, not soluble because calcium is in group 2 instead of group 1. Also, hydroxides are usually not soluble, except again if they're hooked up with alkali metals or the barium ion. Then they do become soluble. So like NaOH is soluble, okay, because Na is a alkali metal, all right, but calcium hydroxide is not soluble because he's in group 2 instead of group 1. So again, you do not need to memorize this table, you just need to know how to use it and need to know when to use it. All right, so here is some for us to try together. So we have to figure out if these guys are soluble or insoluble. So silver bromide. All right, so if we take a look at our solubility chart, bromine is a halide and he's usually soluble, except when he's hooked up with silver, mercury, or lead. And in this case, he is, hooked up with silver. So this guy is going to be insoluble. I'll put IS for insoluble. Calcium chloride. All right, so let's see. Chlorides, again, usually are, these they're part of the halides, and they are usually soluble, except if they're with silver, mercury, or lead. Well, calcium's not one of the insoluble exceptions, so this guy is soluble. Calcium chloride is soluble. All right, moving on to the next, we have lead nitrate. All right, so here on our things, nitrates, okay, are typically soluble, and we don't have any exceptions on this side. Fabulous. Okay, so that means that lead nitrate is soluble. All right, last but not least is lead sulfate, PbSO4. Okay, so sulfates are generally soluble, able to dissolve in water, but they do have exceptions: silver, calcium, strontium, barium, mercury, and lead. Here we have it, lead. So this is an exception. So this guy is insoluble. insoluble. All right, so that's how you're going to want to make sure that you have this handy to figure out if something is soluble or insoluble. And you're going to see that it's going to come in handy when you guys are predicting products of single replacement and double replacement reactions. Woohoo! All right, so let's dig into the types of chemical reactions. And in this lecture, we're going to focus on classifying these chemical reactions via chemical phenomena that we see. So the first one we're going to talk about is the precipitation reaction. Precipitation reactions are a reaction that forms a solid, and the solid we call a precipitate when we mix two aqueous solutions. So over here on the right hand side, we have a solution of potassium iodide and lead nitrate. Okay, and you can see both of those are clear, and when you mix them together, we get, bam, a precipitate. Okay, and so you can see that all of a sudden you get this dramatic yellow cloudy substance when you mix these two together. So this is what we call a precipitation reaction. Now, precipitation reactions do not always occur when you mix two substances together, obviously. So here on the left-hand side is we're going to hook these two clear aqueous solutions together, and we still don't have anything in the middle. So precipitations do not always occur when you mix two liquids together, but when they do, it's pretty cool and it's pretty dramatic. Just a heads up, when precipitate is usually a cloudy substance. It's not going to be like, boom, big chunk or something that all of a sudden falls out of your solution and hits the bottom of your test tube or something. Okay, so precipitates are usually in the form of little particles, like little dust floating, or little like cloud of substance. And a lot of times they're just white, but sometimes they're kind of dramatic, like this guy here. All right, so your job, my friends, is going to be able to predict if a precipitation reaction will form. All right, because we're going to do a lab where you're going to see this, but you're not going to be able to mix these things all the time to verify if a precipitation reaction occurs. You're going to have to look at a chemical equation and predict the products and figure out, is a cloudy substance going to form. So what do we need? What tool do we need to use that? Well, we need to use that handy dandy solubility chart that we were just talking about. Okay, so in order to predict if a precipitation reaction will form, we must know that only insoluble compounds form precipitates. And that makes sense because insoluble compounds cannot be dissolved in water. Therefore, you're going to see them still. Okay, so here is the reaction for what we just saw on the last slide. Potassium iodide and lead nitrate. Okay, and when that reaction takes place, this is going to be a double replacement reaction, meaning that they're going to basically trade partners. Ki is going to trade and become with NO3, and Pb is going to trade and be with iodine. Okay, and so what we get in the products is lead iodide and potassium nitrate. And so what we have to do is look at our solubility chart to see if either lead iodide or potassium nitrate is soluble. So let's take a look. Lead iodide. Iodide, okay, is part of those halides. They're generally soluble except when hooked up with lead. So that's why this guy has a little S by it, because that means that it's insoluble. Okay, so that means a solid is going to form, right? Because remember those, in when we write out chemical reactions, we can either put G for gas, S for solid, AQ for aqueous, or L for liquid. That means pure liquid. All right, and so S means that you're going to have a solid form, and therefore that substance is insoluble. Now, if we look at potassium nitrate's characteristics, all right, nitrates are always soluble, and there are no exceptions. So this guy is still going to become aqueous. We're not going to be able to see the lead nitrate. It's going to be floating around as ions. It's going to be floating around as the K ions, okay, K plus ions, and NO3 minus ions. All right, so they're going to stay dissolved in water. All right, now sometimes we're going to mix two aqueous substances together. Okay, so two substances that are clear because the solids are able to dissolve. And what you get in the end is still a clear liquid. All right, so basically what that means is that the products of the would-be chemical reaction are both soluble. Okay, so meaning that they're both able to dissolve in water and stay as ions. And so when this happens, there's no reaction. There's no chemical reaction that actually takes place. So for example, potassium iodide and sodium chloride. All right, both of these guys, fall under compounds that are, contain alkali metal. All right, and they're halides, right, which are usually soluble, and it's none of the exceptions over here. So what that means is that there's going to be no visible reaction. What's going to happen is that the potassium iodide, okay, is going to dissociate, and you're going to have a bunch of K's and I's floating around in the water, and the sodium chloride is also going to dissociate, all right, and you're going to have a bunch of Na and Cl ions floating around, but they're never actually going to get together because the water is going to keep them apart. Okay, so no reaction occurs when both products are soluble. All right, so let's take a look at writing equations for precipitation reactions. Okay, so there's a couple steps we need to take when writing our equation for these. So we're going to write the formulas of the two compounds being mixed as reactants in a chemical reaction. Then we write the formulas of the potentially insoluble products that could form. Okay, so make sure that you write the correct, charge neutral formulas. So basically it means to crisscross. Remember, crisscross those charges, all right, to make sure that whatever chemical formula you end with is going to be a neutral substance. Okay, then you're not done there. Okay, so like in regular chemistry, we were done. We would just rearrange the reactants to make new products, crisscross, and done. You guys at this level are not done. What we need to do now is look at these solubility rules to determine whether these products are going to be insoluble or not. All right, if the potential products are soluble, you have to write no reaction, because remember, if both of the products that are made are going to be soluble or able to dissolve in water, they're never going to come together to make something that we can actually see. So you have to write no reaction for products that are both soluble. Now, if one or both of the products are insoluble, you need to write their formulas and indicate them as a solid, or S. Okay? And then, of course, last but not least, balance your equation. All right, so here is an example that we've got on this slide. Sodium carbonate and copper chloride come together. Okay, so we can see that we start out with two compounds. So they are going to reorganize themselves. They're going to switch partners in basically kind of like a double replacement reaction. And so sodium is now going to go with chlorine, and copper is going to trade places. All right, and his new partner is going to be carbonate. And so we've got copper carbonate and sodium chloride. Okay, well, if you look at the solubility rules, which I don't have up on screen right now, but if you looked back in your notes, you would see that carbonates are generally insoluble unless they're with the alkalis. Well, copper is not in the alkali metals, and so this guy is going to be soluble, so that's why we write the S. Now sodium chloride, all right, halides like chlorine are always insoluble except if they're with silver, mercury, and lead, and sodium is not one of them. In fact, remember the first solubility rule says that all alkali metals like sodium are always going to be soluble. So this guy is an AQ. Okay, and so we have one that stays dissolved in water, that's sodium chloride, and we have another substance that will actually hook up and find each other, and that is the copper carbonate, and so that's the S. So we will see a chemical reaction here, we will see cloudiness form in a precipitate form because copper carbonate is not soluble. All right, so here's an example. Write an equation for the precipitation reaction that occurs, if any. Because remember, sometimes precipitation reactions don't occur, and so that's what we actually need to find out. So write the equation when solutions of lithium nitrate and sodium sulfate are mixed. All right, and so we've got lithium nitrate here, and we've got sodium sulfate. Okay, so what we'll do is we recognize that, again, these are two compounds that we start with, so they're going to switch partners. Okay, lithium is going to drop the nitrate and go with the sulfate. Sodium is going to drop the sulfate, go with the nitrate. Okay, so our potential products are lithium sulfate and sodium nitrate. And so the next thing we have to do is look at our solubility chart. Okay, so lithium sulfate. So here we have sulfates, and lithium is an alkali metal. Those guys are both soluble. So that means that lithium sulfate is going to stay dissolved in water, AQ. That's what that tries to say, AQ. Okay, so we're not going to get a solid there. Now sodium nitrate, again, nitrates are soluble. There's no exceptions. And sodium is part of the alkali metals, and there's no exceptions there either. So this guy, again, is also AQ. So we're not going to have any solid products here. So we have to write no reaction. Okay, so this is going to be one of the keys in your pre-lab for tonight, for lab number 7, is that a bunch of the ones you're going to have to predict the products and then figure out if they're going to be soluble or not. If both of them are soluble, then you have to write no reaction. If you write anything else, if you hook up Li SO4 and Na3 on the other side, okay, and you basically that indicates that there's going to be a chemical reaction, you will get it wrong. Okay, so please make sure that you always check your solubility chart. You've also have one in the back of your lab manual. It's set up a little bit differently. It's actually kind of easier to use because you just look it up by the positive ion and the negative ion that's hooking up, and it'll either say S for soluble or I think, for insoluble, and there you go. It's super easy. Okay, so please keep this in mind when you're doing your pre-lab for tonight. All right, so let's do one more example before we do a couple of you-try-its. So write an equation for the precipitation reaction, if any, that occurs when solutions of lead 2 acetate and sodium sulfate are mixed. Okay, so the first thing we have to do is write the chemical formulas for lead 2 acetate and sodium sulfate. And here we are. PbC2H3O2, that's the acetate ion right there. Okay, and that is aqueous, so we put an AQ. And then sodium sulfate, Na2SO4, also aqueous, and so we put that there. On the left-hand side is the reactants. Okay, and now we've got to, again, realize we're starting with 2 compounds here, so it's going to be a double replacement kind of reaction where they're going to switch partners. Lead is going to drop acetate and go hook up with sulfate. Sodium is going to drop sulfate and hook up with acetate. So here's our potential products: lead sulfate and sodium acetate. So again, we have to look at our solubility chart. Sulfates are generally soluble except if they're hooked up with lead. Okay, so this guy is going to be solid. So we are going to have a solid in this reaction. Now let's take a look if we're going to have 2 solids. Sodium acetate, okay, is part of this alkali metals, and so they are always going to be soluble. And so this guy is going to be AQ. All right, so what we have to do here then for our products is show them. We hook them up. We make sure we crisscross the charges, okay? And then we have to write the S for solid and the AQ for aqueous. So this one is going to be our precipitate, and this one is going to stay in solution. All right. So that's how that's how it looks when there's actually a precipitation reaction going on, and you see if we were to mix these two liquids together, we would see some kind of cloudiness form. All right, so here's a couple you try it. So what I want you guys to do is pause the video. Okay, so pause the video for a couple minutes, talk about these in your groups, see if you can figure out, and then restart the video and I'll go through the explanations of, if it's a reaction or no reaction, and you can see if you did it right. So go ahead and pause the video and talk about these two with your partners. All right, so I'm back. Here we go. Sodium nitrate and calcium sulfide. Okay, these are both aqueous solutions to start with, and we have to figure out if they're going to have a chemical reaction take place or not. So we start out with two compounds. That means they're going to switch partners. Na is going to go with S, and calcium is going to drop S and go with NO3. So what we do first is we write down the chemical formulas of the potential reactants. So we're going to have NaS, right, and CaNO3. All right, and remember we have to crisscross charges. So Na's got a positive 1, S has a minus 2, so it's actually Na2S. And calcium has a positive 2. And O3 has a negative 1, so it should be CaNO3 with a 2 on the outside of the parentheses. All right, so we got to take a look and see if either of these guys is insoluble. All right, so sodium sulfide. All right, let's see. Sulfides, check it out. Sulfides are here. They are generally insoluble, except when they're hooked up with our alkali metals. So Na is an alkali metal, so this guy is going to be aqueous. Okay. In fact, sodium is up here as well, so he's soluble. Okay, so Na2S is going to be soluble. It's not going to do, any fun for us. Let's take a look at calcium nitrate. Nitrates are here, okay, and they are always soluble. They don't have any exceptions. So this guy, again, is going to be AQ. Okay, so that's not any fun either. Because if they're both AQ, then no reaction takes place because they're just going to be floating around as ions, and we can't see those guys. So we have to write NR, or no reaction. Okay. All right, let's take a look at the second one, magnesium sulfate, hooking up with calcium sulfide. So let's take a look. First, these are two compounds, and so we're going to rearrange their partners. Magnesium is going to go with sulfur, and calcium is going to drop sulfur and go with sulfate. All right, and so our potential products are MgS, positive 2, negative 2, so that's perfect, and CaSO4, again, positive 2, negative 2, so we don't need to crisscross. All right, let's take a look. MgS. Sulfides are going to be insoluble, okay, unless they're with the alkali metals. Well, magnesium is an alkali earth metal, so that means that this guy is going to be a solid, okay, because those sulfides are usually insoluble. Now, calcium sulfate, okay, sulfates are usually soluble, meaning they're able to dissolve in water. They do have some exceptions, and calcium is one of them as well. So this guy is also going to be solid. Okay, so we're going to end up with MgS and CaSO4. Bam. All right, there you go. Let's keep on moving. Okay, so now that you have learned about precipitation reactions and how when you mix some chemicals together, they will make a reaction, and when you mix other chemicals together, it will be no reaction. Well, now we have to learn that or we get to learn, that there are different ways that we can actually write out those chemical equations. So there's molecular equations, there's complete ionic equations, and there's net ionic equations. So basically it's three different ways that you can write an equation for the same reaction. Yay! All right, so let's start off with molecular equation. So a molecular equation is an equation showing the complete neutral formulas for every compound in the reaction. Okay, so here is a molecular equation. Silver nitrate plus sodium chloride reacts to form silver chloride and sodium nitrate. So everything is there. It's the complete neutral formulas. There's no ions shown. We have all the symbols. Bam. That's a molecular equation. That's what you're used to. That's what we just, practiced the first half of the lecture. Okay, so this is what you're used to. Now, we can also show this same exact equation, but using the ionic symbols. So, here, see, oh, yikes. See how we have aqueous, aqueous. What does aqueous mean? It means that it's dissolved in water. It's ions in water. So, we could show this same equation written out in all of the ions. So anytime we have an aqueous, an AQ compound, we would write it out as the ion. So sodium nitrate would be silver. Silver nitrate would be the silver ion written out, the nitrate ion written out. Okay, so Ag plus, aqueous, NO3 minus, aqueous. Okay, and because sodium chloride is aqueous, right, we would also write him out as Na plus for the sodium ion and Cl minus for the chloride ion. Okay. Now on the other side of the equation we have aqueous over here, so we would write sodium ion aqueous and the nitrate ion aqueous. The only place we do not have an aqueous is right here, this solid. So we cannot write that out as ions because they actually find each other, they're attracted to each other, and they hold tight, okay, as a solid substance. So we would have to leave that one as AgCl because that one is not aqueous. It is not just free-floating ions in a solution. It is a solid that forms when this chemical reaction takes place. So this is what we call a complete ionic equation. Dun, 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 dun. See, right here. Complete ionic equation shows the reactants and products as they are actually present in the solution. Okay, because remember, aqueous means that they are free-floating ions. So we have, since both of the reactants were aqueous, we have Ag plus aqueous, plus NO3 aqueous, and we have sodium aqueous, and we have chlorine ions aqueous, reacting to form. Okay, here's our solid. We cannot write that as ions because that's actually solid. They're not free floating anymore. They've found each other. Okay, and they're holding tight. Okay, but the sodium and the nitrate are still aqueous. Okay. All right, so what happens, okay, is that we see a lot of the same ions before and after the reaction arrow, right? So we see the same ions, okay, we see the same ions NO3 on both before the arrow and after the arrow. And we see sodium before the arrow and after the arrow. So basically that just means they're just hanging out there the whole time. They're what we call spectator ions. They don't do anything. All right, they're just hanging out going, yep, I'm still not attracted to you. Yep, still not attracted to you. All right, so they're spectator ions. They have no place in the chemical reaction. They don't matter, actually, in essence. So we can simplify this equation to get rid of these spectator ions that just sit there and do nothing. And we can just show the ions that actually find each other to do something. And which ones would those be? You guessed it. The Ag and the Cl. Those are the ones that we actually care about, because those are the ones that get together to form AgCl, which is our solid. All right, so those are the only ones we care about. So we can simplify this equation to get rid of these spectator ions. And when we do that, it looks so much neater. Okay, so this is what we call the net ionic equation. Okay, net means when you get rid of all the extraneous things that don't matter in a chemical reaction, because they just sit there as ions anyways. All right, when we get rid of all those other ones, we get down to the meat and potatoes of what's actually going on in this chemical reaction. The silver ion and the chlorine ion hook up to make silver chloride. Bam, that's all we need to know. Everything else is just junk. Okay, so a net ionic equation shows only the species that actually participate in the reaction, and that's all we care about. Okay, so that's what we call a net ionic equation. All right, so we've got molecular equations that show just the neutral formulas. We can have complete ionic equations that show all of the ions that are involved in the reaction, and then we can get rid of those stupid spectator ones that don't do anything, and we can just show what's called a net ionic equation. All right, which actually shows what is actually going on that we actually care about, actually. Okay? All right, so let's take a look at one more example. Here we have hydrochloric acid, aqueous, dissolved in water, okay, and sodium hydroxide dissolved in water. Here's our little reaction arrow. And this reacts to form H2O liquid. All right, so pure H2O. Okay, so this guy here is not aqueous. Okay, seems kind of strange because it is water, and stuff dissolved in water is usually aqueous, but this is actually pure water, so that is not AQ. All right, so that means a reaction actually occurs. Okay, so we cannot just write, no reaction for this, because we can't actually see what's going on because there's no like precipitate cloudiness. All right, but anytime water is actually formed in its liquid state, pure liquid state, a reaction has occurred. We've gotten water back. Okay, so please keep that in mind. All right, so here's our molecular equation. HCl plus NaOH reacts to form H2O and NaCl. All right, NaCl again, if we look at our solubility chart, is going to be aqueous. And so that's no fun for us because we can't see that. All right, so because we have a bunch of aqueous symbols here, again, we can write it out as our complete ionic equation. So we can break up the H and the Cl and put H plus and Cl minus. We can break up NaOH, and we have Na, and remember OH is a polyatomic ion, so it has to stay together. Polyatomic ion. All right, so it has to stay together. So OH sticks together. It's a negative charge, right? And then here's our reaction arrow. H2O liquid. Okay, we cannot break those apart. Remember, it doesn't mean aqueous. So H2O stays together. But then we've got NaCl aqueous, so we can break those guys apart into Na and Cl. Okay, so again, we've got a bunch of what we call spectator ions, ions that occur before the reaction arrow and after the reaction arrow. They're the same ones. So for example, sodium and sodium. Chlorines before and chlorines after, right? And so those are our spectator ions that don't do anything, and so we don't care about them, and so we're just going to kick them out. All right, and so the ones that we actually care about are the hydrogen ion and the hydroxide ion that come together to form water. That is our reaction, and so that is what we're going to write down as our net ionic equation. H plus and OH minus react to form H2O. Bam! Just like that. All right, so here's some time for you guys to again pause the video, and write out the complete ionic equations and the net ionic equations for these two reactions. Then you can come back to the video and see if you did it right. So go ahead and pause it. And welcome back. Let's take a look and write out these complete ionic and net ionic equations. Okay, first one. Lead nitrate and lithium chloride react to form lead chloride and lithium nitrate. Okay, and we can see here that we've got a solid. All right, so that means a reaction does occur. It's not a no reaction. So we can write the complete ionic and net ionic equations for these. So for the complete ionic equation, we are going to look at all of these lovely AQ symbols and write out the ions that make them up. So we are going to write out Pb plus 2, aqueous, and we're going to write out NO3 minus, aqueous. All right, and lithium chloride is also aqueous, so this 2 is going to distribute to both of them. So we're going to write 2 Li plus and 2 Cl minus, and I'm going to run out of room, so I'm not going to write the aqueous little symbols anymore, but you get the idea. Okay, and on the right hand side, PbCl2 is a solid, so we cannot break him apart. So he's going to stay together. All right, but we do have another aqueous, Li and NO3. Those guys are ions in the aqueous form. Okay, so that's our complete ionic equation where we break up all the AQs into the ions that form it. Now the net ionic equation, we are going to get rid of the spectator ions, the ions that are present before and after the reaction. So let's just look, we always look at the end of the reaction, okay, and then see if we can match up ones from the beginning. So lithium is a ion in the end, and so we'll cross him out, okay, from the beginning. And nitrate is another ion that's still sticking around, so we're going to knock him off from the beginning as well. And so what we're left with, if we cross all of those guys out, is we're left with our complete ionic equation, which is just Pb, so Pb aqueous, plus 2 chlorine ions react to form PbCl2, that is a solid. Dun, dun, dun. And there you go. That is our net ionic equation. We've gotten rid of those spectator ions, the ones that do nothing, and that's what we have left, the actual reaction. All right, okay, last one, let's take a look at the reaction between hydrobromic acid and calcium hydroxide. Okay, so this is our molecular equation all spelled out for us, and we need to write down the complete ionic equation first. So again, we're going to convert all these AQs into their corresponding ions, and we will make sure that whatever coefficient is out in front also gets out in front of each of the ions. So 2H plus 2Br minus. Then we have a Ca, and calcium is a positive 2, and an OH. And there's 2 of those because we have a 2 right here. All right, and then on the other side of our equation we have the L. All right, and so that means a pure substance. So that means a reaction has occurred. There's no ions there, so we have to leave those intact. Okay, have to leave those intact. All right, but here, over here, there's an aqueous, so we can split those guys up. Ca plus 2 and Br minus, the 2 out front. All right, so next we have to put those spectator ions on the chopping block. So again, look at the products first, okay, and then see if they've got corresponding ones on the reactant side. They always will. All right, so bromine is on the chopping block. He's there before and after. Calcium's on the chopping block. He is there before and after. And so what are we left with? We're left with 2 hydrogen ions in the aqueous form. We're left with 2 hydroxide ion molecules. And they are going to come together to make water in the pure liquid form. Bam! There is our net ionic equation. Beautiful, I know. All right, so all of that had to do with precipitation reactions. So knowing solubility rules and figuring out if a precipitate's going to form, and then knowing how to write the molecular, complete ionic, and net ionic equations for each. So that was kind of a big chunk of our lecture today. So let's look at some other types of chemical reactions, like acid-base and gas evolution reactions. So acid-base reactions form water upon mixing of an acid and a base. Okay, so remember, an acid is a compound characterized by sour taste, the ability to dissolve some metals, and tendency to form H+ ions in solution. Remember, acids will always have their H out front in their chemical reaction, like HCl or H2SO4. Okay, that H out front is our ionizable H, means it breaks off to form an H+ ion. Bases are compounds that characterized by bitter taste, slippery feels, and the tendency to form OH ions in solution. Bases typically, but not always, have their OH in the back of their formulas, like CaOH, NaOH. See, they've got the OH there, but not all the time. Sometimes they are bases because they take an H from water to leave an OH behind, but we'll get there. Okay, so here is an equation, an acid-base equation. Hydrochloric acid plus sodium hydroxide react to form water. So here's our key, right? Acid-base reactions form water upon mixing of an acid and a base. Okay, so basically this is also called a neutralization reaction because we're neutralizing the acid and base by making water, which is a neutral substance. So if you have an acid spill, one way to get rid of it is to neutralize it with a base. Or if you have a base spill, you can neutralize it with an acid. All right, so let's take a look at these. In fact, here we go. Acid-base reactions are also called neutralization reactions, generally forming water and an ionic compound called a salt that usually remains dissolved in the solution. So we can see here that we've got our acid, H2SO4, sulfuric acid, and our base, which is potassium hydroxide, reacting to form water, H2O, and our salt. A salt just means an ionic compound. Ionic compound is also called a salt. Not all salt is table salt, okay, which is the salt we use to season our meat, our food with. Salts could be any ionic compound. So in this case, we have K2SO4, potassium sulfate. All right, and we can see that the salts are always going to be found dissolved in solution. So the salts will always be aqueous. So that's our pattern here for acid-base reactions. Acid plus base equals water and dissolved salt. Bam. So you try it. Write the molecular and net ionic equation for the reaction between aqueous nitric acid and aqueous calcium hydroxide. All right, so again, take a minute to pause the video, discuss with your peeps, and then come back to see if you are right. All right, so molecular equation is just our chemical formulas. So we're going to start off with what we're given, HNO3, and then we say that's aqueous, plus CaOH2, and that is also aqueous. And since this is an acid and a base, we always know that we're going to have water, H2O, and here's where it comes from. It's just like a double replacement reaction. H is going to drop the NO3 to hook up with OH, and HOH is H2O. Okay, so there's where our water comes from. And to figure out our dissolved salt, we take a look at calcium. He's going to drop hydroxide and hook up with NO3 now. So we're going to have CaNO3. And that guy is going to stay aqueous. Okay, so there is our molecular equation. All right, and oh, you know what, let's put an L here to make sure we know that it is pure water. All right, and so what we need to do is also the net ionic equation. And remember, net ionic equation just shows us what we, which parts are actually involved in the chemical reaction, not just spectator ions. So here's a little trick. Whenever you're doing net ionic equations, look for the product on the right-hand side that either has an L or an S. In this case, water is our L. Okay, that's going to be our product, right? And which ions have to make H2O? Well, my dear, H plus and OH minus. Bam, H2O. There you go. There's our net ionic equation. So if you can just identify the solid or pure liquid in the right-hand side and break it apart into ions on the left-hand side, write those out, you got the net ionic equation without going through the hassle of doing the complete ionic equation. However, if the complete ionic equation step helps, please do that, whatever makes most sense to you. All right, so gas evolution reactions are ones that evolve gas, not like evolution like gases come from monkeys, but evolution meaning that they release gas. So we're going to get gas bubbles formed in these types of reactions. So you'll see little bubbles in your test tubes or in your little wells, and that'll be a evidence of chemical reaction. All right, so here is an example. We have sulfuric acid and lithium sulfide react to form H2S, which is a gas, okay, and lithium sulfate, which is an aqueous solution. Okay, so again, figure out how they switch up. Okay, so this is double replacement again. So H is going to drop SO4 and hook up with S. Li is going to drop S and hook up with SO4. We have to always look to see on our solubility chart if anything is going to be a solid. Okay, in this case, this is sulfates, and sulfates are soluble if they're hooked up with a alkaline metal, which lithium is. So this guy is aqueous. And H2S is a gas, and there's not really a good trick to it. You just have to kind of see it or be told, like in the reaction, that it's a gas evolution. And then you can, kind of figure it out. I think in the chart in the back of your lab manual, it might actually say G for gas, but I don't remember. All right. Other gas evolution reactions aren't this simple. They form intermediate products, which then decompose into gas. So like this one, which is hydrochloric acid with sodium carbonate, actually sodium bicarbonate, they call it. And that is going to, again, we're going to see that there's going to be a switcheroo. We're going to have sodium chloride. All right, sodium dropping HCO3 to hook up with chlorine, and then the H going with the HCO3 to make H2CO3. But this is our intermediate. This guy is unstable. H2CO3 is unstable. And so what happens is that it basically breaks apart into water and carbon dioxide. And carbon dioxide is our gas here. Okay, so a lot of the carbonates and sulfates are going to be intermediates for a lot of gas evolution reactions. All right, so kind of look for if something is a carbonate. has a carbonate in it or a sulfate. Okay, actually bicarbonate or bisulfate. Usually they're going to have an intermediate step kind of there, an intermediate product that will decompose into some kind of gas and water. All right, so here is kind of another chart to help you figure out if there's going to be an intermediate product involved with this gas evolution reaction. So, for example, sulfides. Now that's just regular S, right? S hooked up with something. There's no intermediate. Okay, the gas formed is always going to be H2S. Okay, always, if there's a gas formed from it. Now carbonates and bicarbonates, again, like I said, we're going to have an intermediate product that then forms the gas CO2. Sulfites and sulfites and bisulfites are going to have an intermediate product of H2SO3, and then they're always going to form sulfur dioxide gas. Okay, and then last but not least, ammonium. All right, which isn't one we usually see. Ammonium is usually going to have an intermediate of ammonia hydroxide, which is going to fall apart and basically form water and the ammonia gas, NH3. Okay, so again, this is something that you will have on tests and quizzes, so you don't need to necessarily memorize it, but just know that it occurs, and if anytime you see any of these guys here, you recognize that they are intermediate products and you're not done with your chemical reaction yet, you actually need to go that one step further and say what gas will actually be made in the end. So here's an example. Hydrochloric acid and sodium bisulfite, okay, reacts to form, again, H2SO3 and NaCl, right, by double replacement. And so remember that H2SO3 is an intermediate. It's going to fall apart into water and sulfur dioxide gas. Okay, so in the end, you have three products: water, sulfur dioxide gas, and the sodium chloride that was made in that second step. All right, so here's a you try it. So go ahead and pause and try to write the molecular equation for the gas evolution reaction that occurs when you mix aqueous nitric acid and aqueous sodium carbonate. All right, so let's see if you did it correctly. Aqueous nitric acid, HNO3. Aqueous means that's AQ. And aqueous sodium carbonate, Na2CO3, because CO3 is a -2 charge. And that's aqueous as well. And that is going to react to form HCO3 plus NaNO3. All right, and remember that this guy is an intermediate product. So we're going to have H2O plus CO2 plus NaNO3 in the end. All right, so this guy is an L, this guy's the G, and this guy is AQ because of our solubility rules. Dun, dun, dun. All right, there you go. All right, we're almost done, guys. I promise. There's only 4 more slides. We can do this. Okay, oxidation reduction reactions. Or another way we call this is redox reactions. Like redox reactions. Oxidation reduction reactions involve the transfer of electrons. So rusting of iron, bleaching your hair, production of electricity in batteries, all of those, you're transferring electrons to make a new product. So some involve the reaction of a substance with oxygen. So sometimes it's oxygen that's either gaining or losing electrons. So here we've got the reaction, combustion basically, of hydrogen gas and oxygen gas to make water in the gas vapor. And so this is the reaction that powers space shuttles. Wow, over there. And here is another one where oxygen is doing is involved with a chemical reaction of iron, and this is rusting of iron. So iron plus oxygen makes iron oxide. All right, so we can see it rusting right there. All right, so these are examples of redox reactions or oxidation reduction reactions, and we're going to go more in depth with them, but near like the end of the semester. All right, some oxidation reduction reactions do not involve oxygen. So if you don't see oxygen, but it doesn't fall under any other category, then consider maybe looking at it through the scope of an oxidation reduction reaction and see if it works. So usually if oxygen is not involved, then we have a metal reacting with a non-metal to make some kind of product. So basically all metal non-metals hooking up are called oxidation reduction reactions. You never know that before. We didn't throw that at you in regular chemistry because we didn't want to confuse you yet again or any more than regular chemistry was already confusing. So anyways, anytime you hook up a metal with a non-metal on your periodic table, you're doing an oxidation reduction reaction. Okay, because you're exchanging or transferring electrons, which is exactly what the definition we saw on the last slide was of an oxidation reduction reaction. So oxidation means you're losing electrons. So metals are always losing electrons, so they go through oxidation. And reduction means that you gain electrons. So like nonmetals are always gaining electrons, so they're always going through reduction. Now these guys have to always occur together, because guess what? Those electrons have to go somewhere. You can't lose electrons and then they just float away. They have to go somewhere. Even, if, your battery is, powering something else, those electrons are flowing through your electronic device and then back into the battery to, finally stabilize again. So they're reacting with something, okay, along the way. All right, so here is kind of a little analogy, I think they call it, for remembering that oxidation means the loss of electrons and reduction means the gain of electrons. If you remember the, not phrase, but like the object oil rig, you'll remember that oxidation is loss, oil, oxidation is loss, and reduction is gain, rig, oil rig. Wow, that's amazing. All right, so oxidation is loss and reduction is gain. Okay, so like I said, we're going to go much more depth later in this semester with this, but this is just kind of a heads up as to what an oxidation reduction reaction is. So again, it's either a substance reacting with elemental oxygen, has to be elemental, meaning O2 in the reaction, not like CaO, calcium oxide. That's not elemental, so that's not what we call oxidation reduction. It's got to be O2. Or it is, like we just talked about, metals with nonmetals. All right, or more generally, any substance that transfers electrons to another substance is going through an oxidation reduction reaction. So you peeps that are in AP Bio, right, and you're learning about the Krebs cycle and cellular respiration and photosynthesis. Okay, all of those are all oxidation reduction reactions, because all you're doing is keeping track of where those electrons go. So like turning NAD to NADH, okay, is an oxidation reduction reaction. So they happen a lot in your cells through cellular respiration. It's how we get our energy. Through the transferring of electrons. In fact, remember, there's the electron transport chain, right, that goes on in order to get the hydrogens on the other side of the mitochondria so that they can use that diffusion gradient to slap a phosphate on ATP to make energy. Okay, I'll digress. Anyways, it's found a lot in bio. All right, in combustion reactions is where oxygen is reacting, basically something's reacting with oxygen to form an oxygen-containing compound. So these guys are exothermic because guess what? Fire's hot, guys. Fire is hot. Combustion reactions release their heat in as flames of light and heat. So these guys are exothermic. They're hot. So here, look, this is octane. This is the chemical reaction that occurs in your cars every day that you drive them. So we take C8H18, which is octane. We react it with oxygen in the air. That's why you need an air filter in your car to bring in that oxygen from the air and make sure it's clean. And when you get out your tailpipe, you get out CO2. That's why all of the global warming people hate cars. And water in the gas form. Okay, so it's not like, and actually sometimes you see like water or like a liquid dripping out of somebody's tailpipe. That's just the water condensing back down into liquid. Yep, pretty cool. All right, and here's another reaction. C2H5OH. That's propanol? No, not propanol. Ethanol. Ethanol, and so that's like rubbing alcohol. Not really. Rubbing alcohol is propane. It's ethanol. I'm so done. It is ethanol with oxygen to react again to make carbon dioxide and water. So anytime you burn a carbon compound, you always make carbon dioxide and water. Dun, dun, dun. All right, guys, we come to the last one. We've survived. I hope you have too. I barely have survived. Okay, but this is the last slide. This is kind of exciting. So let's do this. Okay, let me fill in these little arrows first because apparently my computer lost the arrows along the way. The arrows didn't survive this long. All right, so which of the following are redox reactions? Okay, so if you print out your notes, then you'll have these. If not, just pause and try to figure out if A, you're reacting with elemental oxygen, or B, you are reacting a metal with a nonmetal, or C, you just have a transfer of electrons, like you're reducing the charge on something, okay? Because that would be the transfer of electrons. So those three things would classify them as a oxidation reduction reaction. So go ahead and pause and see if you can figure it out. All right, let's see if you did it. Okay, so which ones are redox reactions? Well, first one is magnesium with elemental oxygen. Ding, ding, ding. That's redox. The second one is hydrobromic acid with calcium hydroxide. That is not redox. That is not elemental oxygen reacting. It is has oxygen in it, but it's not elemental oxygen. It is not a pure metal with a pure nonmetal, and we can't basically see that there's any charges that are being reduced. So that is not. In fact, if you notice, it's HBr and CaOH, so this is actually acid-base. Okay, this is acid-base reaction. All right, number 3, calcium, which is a metal, and chlorine, which is a nonmetal, reacts to form calcium chloride. Ding, ding, ding. That is a redox reaction because the metal and a nonmetal hooking up. All right, number 4, zinc reacting with Fe2+. Okay, so there's a charge here on Fe. And then in the end, we get zinc with a charge, and Fe has no charge. This, ding, 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 is a redox reaction. It's probably not one that you guessed though. But you can see that zinc starts off with no charge here and ends up with a charge of 2. So that means he lost. So that means zinc is the oil, right? Oxidation is lost, so zinc is oxidized. And Fe starts off with a 2 plus charge, and he goes down to 0. So he gained 2 electrons, so he is reduced, because reduction is gain. Oil rig. Oil rig. All right, so let's keep going because we are almost done. Li plus Cl, metal, non-metal. Hooking up, ding, 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 oxidation, reduction reaction. All right, carbon with elemental oxygen, making carbon dioxide. Ding, ding, ding. Yes. Redox reaction. Fabulous. Okay. Write a balanced equation for the combustion of liquid methyl alcohol. Okay, let's do that. CH3OH. Okay, combustion means you are always reacting with oxygen. So O2. And remember, anytime you burn something or react something that is carbon-based with oxygen, you always end up with what? That is right, CO2 and water. And of course, you're a good chem student, so you'd balance that equation. I'm not, so we're going to leave it at that because we're done. I will see you next class.